Good evening, classroom. We are welcome to my first lecture since since the coronavirus outbreak situation happened and we were forced to go into an online um, version of this classroom. So I hope you guys are all doing good, and I hope you guys are all safe, and I hope you're enjoying your time away from school. I think I, you know, there's going to be more time now. Hopefully, you can spend with your family and at home. um, make the most out of this. And thanks for your some of your emails that you've gone back to me and wishing me, basically safety and health. And I do the same to you. So now, what we're going to be doing. This is the first lecture, and the last time we lectured, we covered. I believe we talked about um, the Reynolds transport theorem. So today we are going to cover briefly the Navier-Stokes equations. So Um, so this is the technology I'm using today, guys. I'm just kind of using a simple blackboard with colors, and let's see how this works out. All right, so this is the Navier-Stokes we're going to be talking about. I already assigned homework. If you, hopefully you got to see it. Um, I'll just write it up here. It's going to be problems chapter 9, 134, 135 through 137, and that's all due on March 20th, which is this Friday. That's because I assigned it on Friday night. But do what you can. If it's a little late, it's okay. If you need the weekend to turn it in, if you need this weekend, then that's fine. I don't think this is too difficult. But if you do get stuck, just let me know. Send me an email, um, and then I can give you some. Since we don't have office hours, we're gonna have to rely on emails for now. And I don't know if there's some other way of holding a virtual office hour. Let me know. We can see what we can do. Okay, so this is the lecture. I'm gonna try to get another lecture this week. It's so happens that uh, I am working from home, but so are all my kids, and so I mean they're all being schooled from home. So it's been kind of a tough transition, right? And so I'll try to have this lecture by Friday at the very least. At the very least, the next lecture at least. So let's see. That being said, let's look really quick since I have you guys here. I wonder if I can go ahead and show you. Okay, that's not what I want to show you. Okay, so what we have is our syllabus, and as you can see, we are in the ninth week, I believe, and that puts us here on the way to midterm two. Now we I just covered Reynolds transport today. I'm covering exact solutions to Navier-Stokes. Next week we'll probably do boundary layer approximations. Then you guys are going to be going on vacation fairly soon, which is the spring break. But anyway, we're not ready for a midterm two. I'll let you know when we're ready for midterm two. At the very least, it's after I cover boundary layer approximations, and then obviously we'll still be on the Corona um, situation when we take our midterm two. So that's going to be taken care of through through a take home situation. So probably like a multiple choice or something. We'll have to figure that out. But anyway, we're not ready for midterm two. We're still at least two lectures away. So I'll give you plenty of time though to prepare. So just stay tuned for that. Okay, so let me go back to the lecture. All right, so I'm going to go ahead and start a new page here. All right, so we're talking again. This lecture is on Navier-Stokes. The Navier-Stokes equations or equation. Now, this is universally used for computational fluid dynamics programs, um, as they handle the flow of a fluid, and it gives you everything from the basically the forces, stresses, everything that has to do with the fluid. It gives us that the CFD program can render from the flow given the boundary conditions. So anyway, when most CFD programs rely on the Navier-Stokes equations, and they're just the CFD programs are solving them, and they have the ability to, of course, model viscosity, non-viscosity, change of density, constant density, but it's universally. What I'm going to do is next lecture I'd likely go into the CFD program that I'm going to be talking about and maybe giving some examples. It's the SolidWorks Fluid Works CFD program, and I can talk to you about what the deconstruct the equation and tell you how the program goes and assumes certain things in order to give you results. So all right, so we're going to go ahead and start the program. So the first thing I want to do is give you Newton's law. Force is equal to mass times acceleration. And this is what we're going to use to basically eventually derive the Navier-Stokes equations. So we're going to divide the force equals the ma, divide by the volume of the particle, so that we work with the density instead of mass. So reverse the terms and place acceleration on the left-hand side. So for that, we're going to do this. We're going to say the density times d volume dt. If you remember that's the material derivative, is equal to the force, which is equal to the force of the body plus the force at the surface. So it's the body force plus the surface force. So we're going to go ahead and give some numbering here. We'll call that equation 1. We'll call this equation 2, just in case we have to go back and refer to it. And so we're talking F is the applied force per unit volume of the fluid particle. That's what this F is, the applied force per unit volume of the fluid particle. So the best way to all Navier-Stokes approximations start with the um, tensor cube. So I'm going to go ahead and do an axis here, and this is the y, this is the x, and this is the z. So the tensor cube involves a cube here in the Cartesian space. Let's see how well I can draw this like that. Not too bad. Okay, and then we have stress tensors that come off of this. So normal to this. Sorry, I pressed the button on my pen that I shouldn't have pressed. Okay, normal to this, what we call the y force. So it's basically the surface normal in the y direction. We know that this is the stress here. We're going to call this tau y y. All right, and then let's just give our normal stresses of our stress tensor. So this is the stress tensor notation we're going to be referring to. This is the tensor cube. So we know this is in the x direction on the x face. So this is tau xx, and the stress that comes normal to this face is tau z z. Now the way we do this tensor notation is we'll say tau is the stress. The first indice is the face that it is applied on. So for example, if we're looking at tau yy, so this is the y face because it's basically normal to the y direction, right? So this is let me go ahead and just change the color over here. This is the normal, right, which is in the y direction. So this is basically I'm just going to say this is the face that it's on, and then the next indice is basically the direction. So I'm going to say D. So this is on the y face in the y direction, right? So I'm going to go ahead and just, because I need to refer back to this, I'm going to go just take all these little extra things that I drew up there. Oops. Just a second. All right, so again, this is, so if you want to go ahead back here. This is the face, and this is the direction. So this is tau x, tau y, it's off of the y face in the y direction. So I'm going to come back to black here, and I'm going to say, well, this here, this tensor now is along the surface. This is more of a shear tensor, and that one is on the y face as well. So we're going to call that, what do we want to call that? I'm going to call that tau. Oh, sorry about that. It's getting pretty small here. I'm just going to say tau y face. And now it's in the z direction, right? So we're going to say tau yz. And now this tensor here is tau y face x direction. Ugh, okay, that's how we do the notation. So if I was going to look at this tensor coming up here on this face, well, this is the x face, right? It's normal in the x direction. So I'm going to say tau x, and it's going up, so it's in the y direction, tau x y. And then if we do another shear tensor here, then that's tau. I'm going to just draw a little arrow here. Tau x face z direction. Okay, so forth and so on. So I can leave it up to you if you want to name this one and this, right? I won't label it, but this is now the z face. So this tau zz is basically, it's the normal face is is the c face in the z direction. So that's why tau zz. So all the face normal to the face tensors are the double indice, tau zz, tau xx, tau yy. So I'll let you name these. You know that this one is tau z y direction. So it's tau zy, tau zy, and this one here is tau z x. All right. So that's tensor notation. Now the other thing, I'm going to do this in red here, is these are differential cubes, so it's just basically an infinitesimal cube. So what we got to do is we have to say that this span here is in the x direction. It's not x, it's actually dx. This span here is, right, you guessed it, dy. And now this span here, so let me see, let me just draw some arrows here just so not to confuse the situation. And this is dz. Okay, very good. So this is our tensor notation. And so what we do for tensor notation is we'll go ahead and we'll say tau, and we're going to say ij, right? So tau ij is, we're going to say this is equals to the stress in the jth direction right? This is the j and the c right here, that one right there. In the j direction, normal to the I-axis. I'll just say normal to ith axis. So that's the face normal to that. So that's the I. All right. Now, what does this mean? Let's see if I can scroll this down a little bit. So what this means is that this is going to be given to us in vector notation, right, as a 3x3 matrix. We're going to say tau xx. Hopefully I don't run out of space here. Tau xy, tau xz. This is tau yx, tau yy, tau yz, and finally we have tau zx, tau zy, and tau zz. So it's z, right? And so that's everything that we drew up here, basically. And so this vector here, for example, is our x direction vector. So it's basically everything that's happening on the x face, which is right there. And this is our second row. is our y face, and our third row is our z face. So that covers everything. Now there are stress tensors on the backside of the cube, so they basically are opposite each face, and they'll have the notations will be a little different, but all you got to know is that um, in order for this stress tensor to stay, when we use some of the forces and it has to stay stable, we got to you have to know that tau ij is equal to the same thing as tau ji, because the on the other faces it's going to be everything. It's going to be the same except switched around. So on the opposite face of this top y face, for example, tau yx on the bottom, its partner way at the bottom here, its opposite face is tau xy. So tau yx would be the same thing as tau xy, and so forth and so on. So that's why we have that there. Okay, so let's go ahead and start a new sheet here. Maybe I'll save this here. Why not? We'll call it S1. All right. All right, so we have a new sheet here. Let me change the color here, just give you guys a little bit of variety here. So what we drew, what I was talking about, the force balance. So the body force of that cube that I showed you, that infinitesimal cube, is equal to density times g. So that's our body force. I'm going to give that equation for here. So why do we say g, and what's the body force? So it's basically the gravity, right? And where g is where g, oh, here we go again. Sorry, I have this this button that I accidentally pushed. So this is g, where g is the gravitational acceleration, right? And it's in the z direction. We always know it's in the z direction. Okay, so let's go ahead and look at all the forces that were. So I went ahead and if you remember the previous picture with the stress cube, the forces that are associated with each face of that cube, let's go ahead and identify those. So we're going to say, since it's in an infinitesimal element, we have dF in the x direction is equal to tau xx dy. Hold on a second. Come on, come in. Sorry, that was my dog was crying outside the door. My goodness. Okay, so so that's tau xx dy dz plus tau yx dx dz plus tau zx dx dy. So if let's go ahead, I feel impelled to go ahead and show you what this is here. Let me just write up all the three equations here. So that's that's the forces in the x direction on that cube. The forces in the y direction are tau xy dy dz plus tau yy dx dz plus tau zy dx dy. And then I'll show you the z direction. Xz dy yz dx dz plus tau cz dx dy. All right, so as you can see, these are our elements. The taus are our elements of our vector, of our tensor notation, that three-dimensional matrix that I just showed you. And these are the faces that they apply on. So that x face that this tau xx applies on is basically defined by a dy dz. So if I was going to go ahead, hopefully this doesn't mess up. But let me go ahead and find that folder. I wish it would just turn up. Let me see, document. And so it would be this one here. Uh-oh, I can't do it because it'll erase this. So basically it's go back to the tensor cube, and these are basically the resultant forces on each face of that tensor cube. Okay. Now we're going to call this equations 5. All right. So now for balance, the front and the back faces are same for acceleration. So so in other words, we have, what does that mean? The front face that I showed you, tau xx, the front part of that cube is equal to tau xx on the back side plus, and now we have the differential stress, which is equal to tau d tau xx, the partial of tau xx with respect to x dx. Okay, so this is just Taylor's series. All right, this just tells us that the next, as we have a progression, continuity, and stress, this would be across that fluid element, or across the fluid element, this would be the increase in stress would be this portion using Taylor's series. All right, and so given that, therefore we have the net force across the whole. Let's see if I can fit everything here. The net force across the whole cube is equal to, right? It's these differential elements, because these other ones cancel out. Txx in the front, Txx in the back cancel out. So what we have left is we have dTxx in the x direction, dx, and then we have the face that they act on, which is dyz, this face here, dy dz, plus the differential, the differential is d tau yz, yx, and this is in the dy direction, dy, and now we have the face is defined by dx dz plus the differential tau zx, okay, d tau zx dz applied on the face dx dy. All right, and so okay, let me go ahead and scroll down a little bit here. That's the net force across that force element. And then say, or a unit volume base. For unit volume basis, we divide by the unit volume. Okay, so if we divide by the unit volume, so we're going to look at the force per unit volume, right? And the unit we're going to basically divide by dx, dy, dz. Now I have to start a new page here. Okay, so therefore now we're going to go ahead and say that if we since, again, we go back to our isotropic cube, which says that stress Ij is equal to stress Ji, and therefore we have the force in the x direction is equal to d tau x dx plus d xy dy plus d xz dz. All right, we're going to call this equation 7. And what does this mean here? This is the divergence, right? So this is equivalent to taking the divergence of the vector tau x, tau xy, and tau yz. So we're actually taking the divergence of the vector the vector in the x direction of the stress tensor of the three-dimensional matrix that I showed you. That'd be that's the top row, x, y. I'm sorry, that's not true. That's tau xx, comma, tau xy, comma, tau xz. We're taking the divergence of the vector in the upper row of the stress tensor. And then similarly, Fy would be the second row of that three-dimensional stress tensor, taking the divergence of that, and F in the z direction would be the third row of the divergence of the vector, the three-dimensional vector. So thus, for the total vector surface force, we have, we're going to make this dark because this is actually in vector form. So the surface force is equal to the divergence of the stress tensor matrix, Ij, which is equal to the partial derivative of tau ij with respect to tau x, and that would be j. So this could be summed up by this stress tensor notation. So we swap indices, and that way you don't have to write basically three equations that have four, or three equations and three unknowns type of situation. Can all be summarized by this vector notation. Okay, we're going to call this 8. Okay, Newton's. So let's talk about Newton's law. We know is equal to force is equal to mass times acceleration, but we can also write, sorry, just crossed it out. I meant to underline it. We can write it, if you go back to the original equations that I wrote, it's the density times dv dt, which is equal to the body force plus what I just wrote here, the force, it's the stress tensor, the divergence of tau ij, right? This is actually Newton's law. And for a hydrostatic situation, this is basically a cube in the bottom of the ocean. We know that tau xx is equal to tau yy, which is equal to tau zz. And we're going to call that, it's basically in compression, so it's minus p, all right, the pressure on that cube. And then we know if it's hydrostatic, we know the off indices, the stresses there are equal to 0 for any I isn't, for all the off indices. So basically where I is not equal to j. Okay, I'm going to start a new sheet here. We're going to call this S3. I don't know why I'm saving these. Okay, well, I guess I'll call it S4. All right, let's change the color here. Maybe we'll give you a nice blue color here. All right, so and we know that the body force, we're going to call that, we're going to call this the gradient of the pressure, which is equal to rho g. All right. Okay, so for the deformation of a Newtonian fluid, the fluid is continuous, the fluid is isotropic. We have an equation for continuity, right? So we know the fluid has to be continuous and it has to be isotropic, meaning that each face is balanced by its opposite face, hence and the strain rates are 0 when the fluid is hydrostatic. Okay, so the strain rates are 0 when the fluid is hydrostatic. So what does that require? So for a hydrostatic situation, there's the off indices are all 0. What does that mean? I.e., That means that if you have your stress tensor, you're going to have you're only going to have strain rates in the down the middle. That's 1, 2, and 3 for X, Y, and Z, and all your off indices are 0. Okay, that's what that means. And these are called the principal strains. And we'll just give that a number 9. And say, for example, we have tau in the 1, 1. So, normally 1 is x, so this would be tau in the xx is equal to minus p plus, we do have stresses on the other faces, so we're just going to say C1 times, C1 times the strain rate on the XX face, or the 1, 1 face, plus a constant 2 times the strain rate on the YY face, plus a constant 3 times the strain rate on the ZZ, or the 3, 3 face. We're going to call that equation 10. And isotropy requires the cross flows be identical. So due to isotropy, this says that C2 has to be equal to C3. And so therefore we have tau 1, 1 is equal to minus P plus kappa E 1, 1 plus C2. So instead of having C2 and C3, we're going to say C2 times E 1, 1 plus E 2, 2 plus E 3, 3. Call that 11. Where kappa is equal to C2 minus, C1 minus C2. So then we say, we note that E11 plus E22 plus E33, these are the strain rates, right? And so this is basically the expansion, the dilation of the cube. And that is actually equal to the divergence of the volume, right? Because this is the volume is basically, it's the differential, or it's how much the cube is stretching, or in this case compressing. That's the divergence of the volume. Okay. Now we're going to go ahead and say, I wonder if I can jump right into. We're almost getting to the derivation, so just bear with me just a second. Let's save this page. All right. So what is this? Okay, so we got to the point where we said that the strain rates E11, E22, and E33 added together is divergence of the volume. Therefore, we're going to rewrite the strain in the x direction, tau xx is equal to minus P plus kappa E x. So instead of using 1, 1, we're going to just go ahead and use our Cartesian coordinates, plus C2 divergence. Divergence of the volume. All right. So these were the components, the E11, E22, E33. And we're going to call that equation 14. I'm not even sure what equation we're on right now, and so we can further, let's see. And so we have, similarly, we can write for tau YY and tau ZZ. You get the point, right? You just replace everything with YY and ZZ, but it's still the divergence of the volume. So now we have to lay out a few rules here. We'll say that tau, the non-normal stresses, XYs, are equal to kappa times strain, xy. Hopefully you can read this. And then we also have to say that tau xy is equal to 2 times mu strain xy, which is basically saying that kappa is equal to 2 mu. Now you're going to see mu later. We're going to refer to mu as the shear, as the viscosity term, and that's associated with the shear, which is associated with the off indice values, basically the ones that are hugging the face, the non-normal strains. Right. So all this gives us. Okay. So if we substitute all this into the Newton's law, we're going to get. You remember Newton's law? We put this all into Newton's law, which was dt is equal to rho g plus gradient dot tau ij. Okay, so if we substitute all that into here, we got the density times du, and u is basically the velocity in the x direction, dt is equal to rho gx minus partial of the partial of p with respect to x plus d dx times 2 times mu du dx plus this thing we call lambda divergence of v. And then we still have the y terms plus d by dy, and then we have mu times du dx plus dv dx now plus d by dz times mu times dw dx plus du dz. Okay. And so that was just in the x direction. We still have to do this 2 more times for the y and the z direction. I'm not going to go ahead and do that because it's too much writing. So now we say, again, you can stop and rewind this video if you need to. But actually, let me go ahead and do the other terms. And you can go ahead and just forward this if this is too much or too monotonous. All right, I don't mind. All right, so that was the x term. The y term is density dv. So remember, for the velocity is, oh, that's pretty bad. Sorry, I might change pens here in the future, but for now I'm just going to say dv dt. This is for the velocity in the y direction. It's equal to the density times gravity. There is no such thing as gravity in the y direction, but just assume there was, minus dp. Now we're doing everything in terms of y plus, because this is remember this is the gradient of p, so now we're doing it in the y direction, plus now we're doing the divergence, dx mu, now say d, oh my goodness. I accidentally pushed the button here. So this is I'm sorry, dv dx plus dv dy plus d dy mu dv dz plus dv dy. I'm going to say plus d by dz times mu. Okay. d by dz 2y dw dz plus that the lambda divergence of v. All right, so I'm not sure if I mentioned this. Yeah, we'll mention this. So actually for the then there's the component in the d in the z direction dt, but we're not going to get into that. Just say it like that. Okay, so then after all that's said and done, we can write this in concentrated vector notation form. So in vector notation, we have now we can just say density d, and then we're going to make this dark d v in any direction x, y, and z dt. The material vector of the velocity is equal to rho g minus del p pressure plus the partial of the x in the j direction times mu. This is the partial vi dxj plus dvj dxi. These are the cross derivatives multiplied by the shear or the viscosity plus the Kronecker delta times lambda divergence of v. This is that darkened vector. We're going to call that equation 18. All right. Now for incompressible flow, what does incompressible flow mean? It means that your density is constant. And for thermal decoupling, so for all that, we're going to say if the fluid is assumed to be constant density, then the divergence of V vanishes due to the continuity equation. So basically, for incompressible flow, we're going to say the divergence of V equals to 0 due to continuity. Right, so to get continuity, you actually have to set the divergence at equal to 0. And so this eliminates the lambda part, as you can see right here. So the lambda part this is called Lemay's constant, if you guys remember that. And I barely remember it, but that's Lemay's constant. That actually goes to 0. That's multiplied by the divergence of V, which is basically 0. And so, and if we assume constant viscosity, so we can say if is equal constant, so we don't have to go ahead and put that into any of we can take it out of the integrals and the differentials. Then we can say that this gives us, now we get to, for constant viscosity and constant density, so we can say, I'll just explain again, is density is equal to constant. Oops. Sorry, my hand's jittery. I drank too much coffee. So now we got, drum roll please. Okay, if I could just find it. Okay, here we go. So we got density, material derivative of velocity, the function of time, sorry, that's dt, is equal to density times g minus the gradient of the pressure plus viscosity times the second grade or the second order gradient times the velocity, right? And this is basically, this is the Navier-Stokes equation. So this is the derivation of the Navier-Stokes equation. It took me 45 minutes to do it, and sorry for all the chicken scratching. I'm trying to get used to this Wacom tablet with my pen that I keep accidentally pressing the bleeding button on. So I apologize for that. But you have the ability to forward the video and to stop it if you want. So anyway, that was the divergence. I'm sorry, the derivation of the Navier-Stokes equation. Believe it or not, this, if we was to handwrite all this in terms of the x, y, and the z direction, it would be many equations, and those are all basically numerically solved in most of the CFD uh, programs that we have. They're all numerically solved. With this, you give it the definition of the grade of the grid, the differential grid, or the finite difference grid, and then you give it a delta t as to how often to do a simulation, how often to do a calculation. So whether it's seconds or milliseconds, and this will actually solve the whole fluid field, including stresses and velocities and such. All right. Well, thank you for attending the lecture. This is the kind of format I'm going to be doing. I may use Zoom in the future to kind of have it up for questions, or you can just look at this, and if you have any questions, you can just email me back. Either way. All right. You guys have a nice afternoon, evening, or morning whenever you looked at this, and we will talk to you later. Thank you.